You're sitting here right now assuming you exist as a clear-cut observer of the world. Quantum mechanics isn't sure you do. It doesn't just question whether you're a reliable observer, it questions whether the facts you record are real. Whether two people can look at the same experiment, both follow the rules of physics correctly, and still arrive at contradictory conclusions about what happened. Not because one made an error, not because they had different information, because the universe, at a fundamental level, may not support a single shared reality. That's the Wigner's friend paradox. And in 2018, physicists Daniela Frauchiger and Renner of ETH Zurich published a formal theorem showing it's not a philosophical curiosity. It's a mathematical proof that quantum mechanics, applied consistently at all scales, produces internal contradictions. Their paper was titled, "Quantum Theory Cannot Consistently Describe the Use of Itself." The physics community has been unsettled by it ever since, and the debate it opened hasn't resolved. If anything, it's gotten sharper. To understand why, you need to go back to the foundation of the problem. Quantum mechanics describes particles not as objects with fixed properties, but as probability distributions. Before you measure an electron's spin, the electron doesn't have a definite spin. It exists in a superposition of possibilities. The act of measurement collapses that superposition into a single outcome. The electron is spin up or spin down. The probability wave is gone. A definite fact exists. Niels Bohr and Werner Heisenberg formalized this at the 1927 Solvay conference. It became the Copenhagen interpretation. Measurement causes collapse. Before measurement, reality is undefined at the quantum level. After measurement, it's fixed. This interpretation has survived nearly a century because the predictions it generates are spectacularly accurate. It predicts experimental results with more precision than any other physical theory in history. And it's not just close. The agreement between theory and experiment in quantum electrodynamics, a branch of quantum mechanics, reaches 12 decimal places. That's the equivalent of predicting the distance from New York to Los Angeles to within the width of a human hair. But the theory has a problem it is never fully answered. What counts as a measurement? What constitutes an observer? The Copenhagen interpretation says measurement happens when a quantum system interacts with a classical measuring device. But nothing in the universe is actually classical. Everything is made of quantum particles. The line between quantum and classical is drawn by hand, and both Bohr and Heisenberg knew it was arbitrary. Bohr's response when pressed on this was essentially that the question was meaningless. You shouldn't ask what's happening before measurement, because before measurement there is nothing to describe. The theory describes outcomes, not underlying reality. Accept the predictions and stop asking what's really there. That answer satisfied enough people for long enough that the problem stayed buried. In 1935, Erwin Schrödinger tried to expose that arbitrariness with a thought experiment everyone has heard of, but fewer have thought through seriously. A cat in a sealed box, a radioactive atom that may or may not have decayed, a mechanism that kills the cat if the atom decays. The atom is a quantum system, so before you open the box, it's in superposition, decayed and not decayed simultaneously. The Copenhagen rules say the wave function collapses when observed, but the cat observes the outcome. The cat is made of atoms. If the rules apply universally, the cat should be in superposition too, dead and alive at the same time. Until you look Schrödinger didn't believe cats were literally in superposition, he believed something was wrong with Copenhagen. The experiment was meant as a reductio ad absurdum, an argument meant to expose a flaw by following the logic to an obviously wrong conclusion. But the physics community largely agreed to treat the cat as a classical observer and move on. The problem was real, but nothing in the theory broke when you ignored it. Then, in 1961, Eugene Wigner took the problem one level higher. Wigner's thought experiment placed a friend inside a sealed laboratory along with a particle in superposition. The friend measures the particle and gets a definite result. From the friend's perspective, the wave function collapsed. A fact exists, but Wigner is outside the lab. From his perspective, the entire lab is a sealed quantum system. He hasn't interacted with it. So from his perspective, the wave function has not collapsed. His friend is in superposition. One version of the friend saw spin up, another version saw spin down, and both possibilities persist simultaneously. Two observers, same experiment, opposite descriptions of whether a definite fact exists. Both are following the rules of quantum mechanics correctly. Wigner published this in a chapter called Remarks on the Mind-Body Question and concluded that consciousness must play a special role in collapse. Only a conscious mind could genuinely force the wave function into a single outcome. That was his escape. Most physicists found it uncomfortable and rejected it, but they couldn't offer a better answer. The thought experiment settled into the category of interesting puzzles and stayed there for decades, treated as a curiosity, not urgent. That changed in 2018. Frauchiger and Renner didn't just redescribe the scenario, they formalized it into a proof. They constructed an extended version of the Wigner's friend setup with two Wigners and two friends, and they showed that when you run the scenario to its logical conclusion, the framework collapses. Their paper identified 4 assumptions that any sensible quantum mechanics would need to satisfy. First, quantum mechanics applies universally at all scales. Second, observers can use quantum mechanics to predict other observers' measurement outcomes. Third, when an observer gets a definite measurement result, they can treat that result as an established fact. Fourth, if 2 separate chains of reasoning both lead to the same conclusion, that conclusion holds. These aren't exotic demands. They're the minimum requirements for quantum mechanics to be a consistent, self-describing theory. Frauchiger and Renner proved that all 4 cannot simultaneously hold. In their scenario, 2 observers following the rules step by step reach mutually exclusive conclusions about whether a specific event occurred. One observer's conclusion is that a particular outcome did not happen. The other observer's conclusion is that it did. Both derivations are valid. Both follow from quantum mechanics. Neither made an error. The result doesn't tell you which assumption to abandon. It just tells you that one must go. And the physics community has been arguing about which one ever since because every option is costly. The many worlds interpretation offers one exit. Hugh Everett proposed it in 1957 as a response to exactly this kind of problem. He was a graduate student at Princeton at the time, and his advisor, John Wheeler, found the idea simultaneously compelling and professionally risky. In Everett's picture, there is no collapse. The wave function never collapses. Every possible measurement outcome happens, but in separate, non-interacting branches of reality. Wigner and his friend don't contradict each other because they inhabit different branches after the measurement. Each branch contains a consistent, self-contained version of events. The contradiction between observers dissolves because the observers are no longer in the same world. The mathematics is coherent. No collapse mechanism is needed. The the contradictions vanish. But the price is accepting that every quantum measurement literally splits reality into parallel copies, that all those copies are equally real, and that we can never access or detect any branch except our own. Every time a physicist measures an electron's spin, the universe bifurcates. One branch has spin up, one branch has spin down, and both branches continue forward with no knowledge of each other. There's no experimental test that distinguishes many worlds from Copenhagen. Any result that confirms one confirms the other. It's a complete physical theory that is, by construction, impossible to falsify as currently understood. Many physicists find that an unacceptable position for a scientific theory to occupy. Čáslav Bruckner of the University of Vienna proposed a different answer. In a 2018 paper responding directly to Frauchiger and Renner, he argued that the third assumption has to go. The assumption that a measurement result constitutes an objective fact. In Bruckner's view, facts are observer relative. There is no single truth about a quantum measurement result that exists independently of the observer recording it. Two observers can hold contradictory facts about the same event, and both are correct within their own reference frames. This connects to relational quantum mechanics, a framework Carlo Rovelli developed in 1996. Rovelli's position is that quantum states are never absolute. They're always defined relative to some observer. The universe doesn't have a view from nowhere. Every description is a description from somewhere by someone. And there's no meta level where all those descriptions get reconciled into one objective story. Rovelli draws an analogy to velocity. There's no such thing as absolute velocity, only velocity relative to some reference frame. He argues quantum states work the same way. The spin of a particle isn't spin up in some absolute sense. It's spin up relative to the measuring device that interacted with it. A different observer who hasn't interacted with the system can consistently hold a different description. That idea has real consequences outside the lab. If observer relative facts are the correct way to understand quantum mechanics, then the universe isn't a place where objective truths sit waiting to be found. It's a place where truth itself is indexed to the system doing the observing. Most physicists resist this. It sounds like it opens doors that physics has spent centuries trying to close. But the math keeps pointing in that direction, and resistance isn't an argument. And here's the part no one likes to talk about. In 2019, Massimiliano Prietti and colleagues at Heriot-Watt University built a real physical implementation of the Wigner's friend scenario using 6 entangled photons. This was experimental, not theoretical. Their paper, published in Science Advances, confirmed the core prediction of the Frauchiger-Renner Theorem. 2 observers in the setup recorded contradictory measurement outcomes, and statistical analysis verified that the contradiction couldn't be explained by hidden errors or random noise. The incompatibility was confirmed at more than 5 standard deviations. That's the threshold physicists use to declare a result real. The experiment ran thousands of trials. The contradiction wasn't a fluke. It reproduced, and it matched what the theorem predicted. Defenders of the Copenhagen interpretation pushed back. The objection was that the friend inside the box in Prietti's experiment wasn't a conscious observer, just a quantum measuring device. So the contradiction observed was between devices, not between genuine minds. The experiment tests the mathematics but doesn't settle the question of whether consciousness plays a role in collapse. That objection, though, cuts in a direction its proponents may not want. If you say the experiment doesn't count because no conscious mind was inside the box, then you're conceding that consciousness matters for wave function collapse. which is exactly the answer Wigner himself proposed in 1961, the one the field spent 60 years rejecting. The fourth escape route, the one Einstein favored, was to say quantum mechanics is incomplete, that there are hidden variables beneath the probabilities, real definite states that exist before measurement, and quantum theory just doesn't have access to them yet. Einstein held this position until his death in 1955. It was elegant, it preserved objectivity, it kept facts as facts. It was also ruled out. John Bell proved in 1964 that any hidden variable theory must be non-local. It must allow influences that connect entangled particles across space in ways that can't be explained by anything traveling between them. Alain Aspect and colleagues confirmed this experimentally in 1982, showing that measuring one entangled particle instantly determines the properties of its partner regardless of the distance separating them. The correlation is too strong to have been built in beforehand and too fast to be a signal traveling through space. Subsequent loophole-free tests in 2015 and 2016, including by Ronald Hansen's group at Delft University of Technology, closed the remaining objections. The universe is non-local in a measurable, confirmed, repeatable sense. Einstein's preferred solution is gone. And non-locality alone, without some additional framework, doesn't tell you how to resolve the measurement problem. It just adds another layer of strangeness to it. So the paradox has 4 exits, and each one opens into something harder than what you started with. Either reality branches infinitely on every quantum measurement, or facts are local to the observer, and 2 people can hold contradictory truths simultaneously, or collapse requires something the theory can't describe, or the universe is non-local in ways that still don't resolve the measurement problem cleanly. What physicists agree on is this: the theory works. Every prediction holds. Every experiment confirms the numbers. The mathematics is correct about everything measurable. And at its own foundations, at the level where quantum mechanics tries to describe the act of observation that makes it work, it produces a contradiction. Frauchiger and Renner didn't write their paper to cause trouble. They wrote it because they were trying to understand what quantum mechanics actually says when you take it seriously all the way down. What they found was that taking it seriously all the way down breaks it. You've been walking around your whole life, assuming that when you observe something and record a fact, that fact exists independently of you, that it would be true whether you looked or not. Quantum mechanics, applied to its own observers, says that assumption may not hold at the level where reality is actually constructed, which leaves a question the field can't currently answer. If 2 observers following the same rules can reach incompatible conclusions about the same event, what exactly is physics describing?